The words such as cheap and CNC plasma table generally don't go together in the same sentence, but let me show how you can get into CNC plasma cutting for pretty cheap and with some impressive results. If you do any kind of metal fabrication, then you know that a welder is one of those tools that you just cannot live without. And I came to that same realization when I picked up this plasma cutter a few years ago. It's one of those tools that once you use it, you'll wonder how the heck did you get by without it all the time before? Especially now when you can pick up a Chinese machine between $200 and $300. Plasma cutter by itself is great if you're just making some simple cuts. For example, if you're making just a straight cut where you're using a straight edge to ensure that you will cut in a straight line. And you can also use it to cut some basic simple shapes. And cutting intricate shapes out of sheet metal with high precision is something that's been on my bucket list for a really long time. Because let's face it, who doesn't want to build their grandma a nice shelf for Christmas with some cool intricate supports? I know I do. So in order to achieve something like that, you need a computer numerical control, or CNC. CNC is a machine that's being controlled by a computer to guide a cutting torch along pre-programmed path. And the main reason that I never got into CNC is because of the price. It is generally really expensive. I think I got a workaround for that. It will definitely have its limitations, but it is so cheap that there's no way I'm going to complain about those limitations. So what's in the box? As you can tell, some of the components had been just thrown into the box and they look like they are used. And that's because to save a few dollars, I actually picked up this machine secondhand. This is a CNC laser engraver. Whenever I'm trying to build something, I always challenge myself to do it as good as possible while keeping the cost as low as possible. This way, I feel that I get more value out of my creation, and also I don't make much money off of these videos. So that's another reason why I went with a second-hand laser engraver to keep the budget costs down for this build. Our CNC table is basically done. It is not quite ready to accept the plasma torch just yet, and we will address that shortly. But first, let's go ahead and set up our plasma torch. I know some of you will probably wonder what is the brand and model of the plasma cutter that I'm using. It is a Thermal Dynamics Cut Master 42. I picked up this unit about 6 years ago, used for $250. And that was a steal of a deal back then. And even today, if I found one of these machines for that much, I would grab it without giving it a second thought. This is a name brand machine, and back when I picked this thing up, there wasn't any cheap Chinese plasma cutters on the market. Therefore, name brand was the only way to go. And today, you can pick up a capable Chinese machine for about $200 to $300 that will meet most of your needs. By default, all of these plasma cutters come with a hand torch. Hand torches can be adapted to run on CNC tables, but for better cut quality, most professionals will use a machine torch with their CNC setup. The frame of this laser engraver isn't very robust, but that's because it was designed to only support the weight of this laser head, which weighs almost nothing. This hand torch doesn't weigh a whole lot, but if it is mounted on that laser engraver, the handle swings outward, and also coupled with the weight of the cable, it will experience some lateral forces. The weight of this broom is trying to rotate my wrist downward, but if this broom is set in a vertical position, then I no longer experience that lateral force. And I bet you that the lateral force of this hand torch in a horizontal position is enough to put some twist on a frame of this laser engraver. This way, the plasma arc that would be coming out of the tip will no longer be pointing straight down. Due to that slight twist, it may face slightly off to the side, and that will definitely affect your cut quality. That's why I decided to go with a machine torch. After looking around online and seeing that the machine torch goes for about 3 times as much than what I paid for my entire plasma cutter, I figured, what if I just look for machine torch components and build my own machine torch? if you were to convert your existing hand torch to a machine torch, you already have most of everything that you need right here. You got your plug, you got the cord, and the only thing that you would need is just the machine torch body with all of the internal components. After looking around online some more, I didn't really have a whole lot of luck finding components to build a thermodynamics torch. However, what I did find were components to build a Hypertherm brand machine torch. And for those of you who don't know, Hypertherm has been around since the 60s, and they've been on a leading edge of anything that has to do with plasma cutting technology. So they are as good as it gets in the world of plasma cutters. I know my main power unit is still thermodynamics, but something tells me that if I am successful at adapting that Hypertherm machine torch onto my existing plasma cutter, I may end up with a superior cut quality even to the thermodynamics torch. And to be honest, I don't even know if I can mix and match all these different brand components to make them work together, but I would definitely love to find out. And another thing worth mentioning is there is quite a bit of aftermarket support for Hypertherm machines, and I don't mean just consumables. You can actually get a lot of torch parts aftermarket. I did look around, but I wasn't able to find anything aftermarket for thermodynamics torch components. Name brand hand torches are ridiculously expensive. You can buy a brand new Chinese plasma cutter that already comes with a torch for way less than what just the name brand torch goes for. And this is why I wouldn't just go out and spend all that money just to buy another torch to convert. But sometimes a great deal that you just cannot pass up falls in your lap. About 2 weeks ago, I was picking up some food at this little restaurant down the street from my house, and while waiting for my food to get ready, I walked over to a pawn shop that was located literally right next door to the restaurant because I had few minutes to kill, and also I wanted to see if I could find a worthy replacement for an old DeWalt drill that recently went out on me. I didn't feel like dropping over $200 on a brand new unit. And while browsing around in a tools section, out of all things, I come across this thermodynamics hand torch just hanging on the nail on the wall, and I was able to get it for so cheap, I just couldn't pass it up. At this point, some of you will probably wonder, why would I even bother with having to go out and look for another torch when I already have a torch that I can go ahead and convert? As I'm filming this video right now, I have no idea if I'll be successful with this conversion. This is an uncharted territory, even for me. So in case I totally destroy my original torch, I don't want to end up with a plasma cutter that is totally unusable, because now I don't have a functioning torch to go with it. So check this out. Originally, Pawn Shop wanted to sell this torch for $199.99. And after it did not sell for a while, it got discounted down to $50. At the checkout, one of the Pawn Shop employees told me that they actually had this torch for over 2 years. And since they had it for so long and it didn't sell, I knew that I could get even better deal than that $50. Long story short, I walked out of there with a torch and a drill, all together for $50 out the door, and you just can't beat that. Since these drills go for about $50 in used condition, means that I got that torch for basically free, and who doesn't like free stuff? I know I do. This torch is identical to the torch that's currently attached to my machine, which means that it's going to be a direct plug and play, requiring only the cutting edge of the torch to be converted. And here are all the components that we'll need to make it happen. Well, mostly things that are circled in the front row, and this guy right here. The rest of the components that you see on the table are just consumables. My understanding is that all of these torches are basically going to be the same no matter what the brand is. They all work on the same principle. The main differences between the handheld torch and a machine torch is the hand torch will cut at an angle while machine torch will cut straight down, and also hand torch has a manual trigger that you have to depress in order to start the cut, while machine torch is going to get activated by the computer. So what's going on inside of this torch? Let's find out. Luckily, these things are pretty easy to open up. There's not even any screws that are holding this thing together. This is actually a pretty simple setup. We got a couple of switches here. This switch gets activated by the trigger. The second switch ensures that torch will not fire unless this shield cap is on there nice and tight. Then we got the main body of the torch that's connected to an air tube and also 2 power wires. And that's it. That's actually really simple. For our conversion, the main items that we need is the replacement main body. We're gonna need this barb fitting to slide our air hose over. Then we have this switch that plays the role of a switch in here to make sure that the shield cup is seated all the way. There is a plunger here on the side, and as the shield cup pushes on it, it will push it up and close the switch, and that will let the plasma cutter know that all of the consumables are installed. We've got a couple of cutouts here on the side. One of them is pretty close to this plunger, and that's where the switch will go, where it will also get attached with a provided screw. And the notch on the other side is where the pilot arc wire goes. Everything hooks up just the same on our new torch as it was on the original hand torch, where this red wire is the original pilot arc wire and it's crimped onto the head portion of the original main body. And I'm gonna have to figure out a good, clean way to have a nice, solid connection here. Another thing to note is this plug on the switch. Since I don't have a corresponding plug, my very first thought was to just cut this plug off and solder these wires on. But I don't really want to do that because I want to make this serviceable, meaning I want to be able to quickly disconnect this thing if I have to service my torch, and I don't really want to deal with cutting wires, so instead I want it to be just plug and play. Once upon a time, this used to be my wife's frother for the cream that she would put in her coffee. It crapped out at some point, and I figured I'm gonna go ahead and fix it. I took it apart, then I got sidetracked by something else, and this frother just been sitting in this state for the past few months. And after taking a quick look at it, I did see some items in here that I could salvage and use in my torch, particularly this little wire right here. This connector perfectly fits into this recess, and it gets firmly attached in place with another provided screw. So I got the pilot arc wire handled, but how am I gonna make this connection right here? I decided to try my luck by going through the box of random wires that I got sitting around, and what do you know? At the very bottom of the box, this is what I found. I believe this belonged to a car audio system that had an optional backup camera hookup, and this wiring came with a small 4-prong plug. I figured that maybe I could modify this plug to make it work with this one. This plug has 4 prongs and it has this little hook, while this plug has a 2-prong receptacle with a little catch to catch a hook. Imagine my surprise when I put these 2 plugs together. This fits amazingly well. It looks great, but does it actually work? Are we making a good contact in here? So since our connection happens in this upper row, that means that we should be using this black and red wires. Let's quickly check continuity between those 2 wires. To free up my hands, I'm gonna use some alligator clips. Testing all of your connections as you go along really pays off in the long run. Just because those 2 plugs click together doesn't necessarily mean that the wires inside made a solid connection. And the beeping confirms that the connection is good. This purple wire isn't connected to anything. We don't need it. Let's cut it off. Whenever I take anything apart, I don't ever destroy it. I always try to be minimally invasive, so if I were ever to put this torch back to its original state, it would take minimum amount of effort and time to complete the task. These original hand torch components are much too valuable to be simply discarded, therefore nothing gets thrown away, and on top of that, there is no guarantee that my new setup is going to work. So I'm putting all of the internal components back in their original location and putting this hand torch away for safekeeping. So inside of this cable, we have an air tube, 2 power wires, 1 pilot arc wire, and 2 trigger wires. But wait a minute, we had 2 switches inside of the torch handle. Well, that means that both of those switches were running in line with each other, and both of them would have to be in a closed position in order to close connection between these 2 wires. So if one or both of those switches were in open position, there would be no connection between these 2 wires. On my original torch, these blue power wires were crimped on to this air tube, and my new barb fitting came with these crimp clamps. I'm gonna have to cut this air tube back a bit to make provisions for this barb fitting. And I also wanted to expose the blue power wires by a good amount. I was able to get this barb fitting about 3/4 of an inch or so into our air tube. I purposely kept these leads this long so this way I can wind them around the barb fitting and bridge the gap between the clamp and the fitting itself. And once I got everything crimped up, I got a pretty solid wire to barb connection. At this point, I can attach the main body of the torch so I could finalize the lengths of all of our wiring. Pilot arc wire is way too long. Let's shorten it. After cutting out the center of the wire and joining both ends, this is what I got. Next up, for that good solid connection, I soldered the switch plug into place. And this is where I got a bit ahead of myself. I will explain my mistake in just a bit. Alright, as far as I'm concerned, at this point in time, everything is done right, and I'm finally ready to get this torch fully assembled. Spade connector for a pilot arc wire is fully seated. Next, I made sure that all of our air connections were nice and tight, so we wouldn't have any air leaks. And lastly, the retaining cap switch gets connected. We're almost there. The only thing left to do is to install the outer sleeve, where its front section gets attached to the main body with 3 screws, and the sections of the sleeve that follow simply thread into the section that went in before it. And just like that, this torch is basically all done. The only thing left is to install all of the consumables. Electrode that goes inside of the swirl ring get installed first, followed up by the nozzle and the retaining cap, and the last piece that goes in is the shield. It's all assembled and looking beautiful, and this is when I realized that I totally failed to make the provisions for the trigger wire. And to fix that, I unsoldered one of the wires that went into the retaining cap sensor plug and spliced in 2 extension wires into that spot. One of those extension wires got soldered onto the wire that came out of the plug, while the other one got soldered onto the trigger wire that went back to the plasma cutter. Okay, this is the way it should have been done first time around. Torch gets assembled same way as before, with the exception of feeding the trigger wires through the sleeve and through this plastic strain relief. I hope I got everything assembled correctly, so let's go ahead and test it out. Everything is ready to go, so the only thing left is to connect these 2 trigger wires to close the circuit, and that should activate the torch. I'm gonna use this push button starter. Can you tell I'm getting pretty excited right about now? Awesome! That worked! I did have my doubts, but it worked out. So the next challenge now is to get this torch mounted and operational on our CNC table. Let's measure out the width of the outer sleeve, and we're right at 35 millimeters. A couple of years ago, I had a project where I had to buy a couple of 35 millimeter rifle scope rings. You would use these to mount a scope on your rifle, and at the time that I bought them, they ended up being the wrong size for the project at hand, but in the end, they worked out perfectly for this project. At this point, there's still no way that I can mount this torch onto our CNC table. The only thing that I don't have that would go in between the scope ring and our CNC table is the scope mounting rail. I don't have a couple of days to wait for the rail to get delivered, but what I do have is a 3D printer, so I'll just print me a rail. It's really simple. Just go to a website such as Thingiverse, type in what you're looking for, and browse through endless variations of that item. Pick the one that you think would fit your application the best, download it, and print it. After about an hour of printing, this is what I ended up with. But will it work? It fits really snugly. There's no gap in between the ring and the rail itself. For alignment purposes, I'm going to use this laser head mounting plate, because this thing was precisely made to be fitted on the laser engraver, and it's made in such a way to where this mounting rail is going to be 100% perpendicular to the work plane, which is very important if we're trying to achieve the best cut quality. The rail that I printed is pretty small. It doesn't even fill the entire length of this metal rail. It also got these features on the bottom that protrude. We definitely don't want these for our application. We want this bottom to be just nice and flat. I can kind of have it seated inside of this recess, but as you can tell, it's not perfect. There is a gap there, and also this rail has quite a bit of movement side to side. I quickly printed it out just to kind of get an idea as to what I should be expecting with a 3D printed rail. But obviously this rail isn't going to work, so let's design a better one. First, I'm going to take measurements of our original metal rail, so this way we would ensure that our newly printed 3D rail would snugly fit inside of it. So let's go ahead and look up the actual dimensions of the Picatinny rail. Click on Images. I already looked at a lot of these schematics, and the image that I found to be the most useful in our case is this one right here. The website I'll use to design our rail is called Tinkercad. Tinkercad is free and is pretty easy to learn. It uses simple shape blocks like something that kids would use. You manipulate and stack these shapes together to make new shapes. I was able to design this Picatinny rail just after watching a handful of YouTube tutorial videos, and as a result, I got exactly what I was looking for. But since this video is not about how to use Tinkercad, because that would take a while, therefore, I'm not gonna take a deep dive into how to use this program, and instead I'll just do a quick time lapse where I will skim over the more major parts of this design process. If you guys like to tinker and build stuff and you don't have a 3D printer, I would highly recommend you getting one. You can pick up used ones for next to nothing. I paid 40 bucks for mine, and it is definitely a useful tool to have around. The fitment of the newly printed rail is really tight all the way around. Now let's get it permanently attached to the laser mounting plate. All scope rings are going to have this ridge. It is a lock. It is there to ensure that the scope won't slide back and forth due to recoil on the rifle. I need the ability to slide the torch up and down the rail, but as of now I can't even mount this ring onto the rail because that locking ridge is getting in the way. I gotta get rid of it. I could use a file to shave down that ridge, but I have a mini mill, so I think I'll use that instead. Yep, it fits great. The torch is in and everything is feeling and looking great. So at this point, the last thing we gotta do is to get this torch wired into the laser engraver, so this way it would fire on command. This plug plugs into the laser, and that's how the laser gets powered up and also triggered to fire. We got 3 wires running into the plug: red, black, and white. The red would be positive, black is negative, and white is a signal wire. There's obviously no way for us to just plug our torch straight into this plug. We have to have something in between. And for that, I'm going to use this relay. So this would be the side that the plug would be going into. We have our DC positive, negative, and the signal in. On the back side, this is where our trigger wires from the torch would go. We've got an NO, which stands for normally opened, and C, which is normally closed, and common. The only bad thing about this relay is that I don't have a way to actually plug this plug right into it. The way these connectors are set up, you basically have to feed a stripped wire into an opening here and then crimp it down with a screw. I don't want to just cut this plug off. I want to keep everything original. I personally hate hacking up the wiring on original equipment. This way, if I ever do have to use a laser, I can just plug it in and go. And that's the main reason why I don't want to cut this plug off just to get it adapted to this relay. So I'm going to modify this relay instead. If we look at the side of this switch, we have this little jumper here with 3 prongs coming out of it for high and low. Now, I'm not sure what high and low really does. When I bought these relays, I actually bought 6 of them for the price of just 1, which is a good thing because now I have some sacrificial relays. First thing I'm going to do is desolder our input port and also this little guy right here. Now, let's quickly modify the pins so that our new plug receptacle would match the footprint of the original larger one. Modifications are done. This is more like it. And I think as far as the placement of this relay goes, it actually fits really nicely right back here. So red goes to DC plus. Beautiful. And to connect the trigger wires on the torch, we're gonna put one of these wires into the center post, which is common. Normally open is the port that the second wire goes into. I pulled the torch off because I did not want it to set this cardboard on fire and also blast holes through my welding table that's just below this cardboard. To control this laser engraver, I think by default you're supposed to use a software that's called Lightburn, but since plasma cutting process is going to be slightly different from laser engraving, I'm not sure if I can get away with using that same software, but don't quote me on that. So instead, I'm going to be using this Open Builds program. I'm running everything on an old laptop that I had sitting in my closet for a while. I've already preloaded a G-code for a simple file that we're gonna run just for testing. I will explain the workings of the software side of things in just a bit. The torch seems to be engaging right when it's supposed to, so I think at this point we are ready to start making some cuts. But I don't want to set my backyard on fire, so I am going to use this water table that I've acquired a while back along with a bunch of other tools. And luckily for me, this water table came with these slats that are actually meant to be used with a plasma cutter, so I will gladly utilize them. I'm gonna attempt to cut into this 1/4 inch or a 6mm steel plate. And for some edit support, I will drape my torch cable right over the stand that I normally use whenever I paint some car parts. If I had a Z-axis on this machine, meaning if I had a setup that would allow for this torch to go up and down, then I wouldn't have to manually set up the gap between the tip of the torch and the surface of the workpiece. Generally, the tip of the torch has to be about 3.5mm above the surface for pierce height. But then once the metal is pierced, the torch would normally move down to about 1.5 millimeters off the surface. And that's the correct way of cutting. But since this laser engraver does not have a Z-axis, and it will not automatically move up and down, that means that I have to manually set the tip of the plasma torch about 2.5 to 3mm off the surface, and that should cover our pierce and cutting height. Also, I feel like that as I'm cutting, I don't want the sparks from my cutting area to shoot up and bounce off the shield and possibly short something out on the circuit board that's behind this cover. I think it would be a wise idea to get this removed and move it off to the side. But before we get it out of the way, let's first plug it into the power outlet and power it up. Lastly, the laser engraver gets connected to a laptop through a USB cable. And now let's get this controller out of the way. I've got the Open Builds up and running, and it's going to fully control our laser engraver plasma table. Now let's connect. The name of the connection on my MacBook comes up as this USB modem, so let's connect to it. But if you're on the Windows machine, then your connection name might be something like this COM3. Once we're connected, let's open up our cut file. This is something I just quickly designed on the fly. I will explain how I got here in just a minute. With the cut file loaded, you can use these arrows on the screen to jog the plasma torch into position. Once the torch is in a good spot, you can go ahead and zero out its position, and now you can start cutting. And my very first cut did not go as planned. It was a pretty big fail. Second cut went a lot better than the first one, but still not great. I sped the footage up a bit for the sake of time. The sections that were supposed to be cut out were still pretty firmly attached. And the third cut was by far the best one out of all three. I was still tweaking the settings and dialing things in as I was moving along, and with each cut, the cut quality was getting better and better. So let me quickly go over everything that you just saw. I'm using Fusion 360 to generate the shape that I just cut out. If you Google it, the search will actually take you to an Autodesk website, and that's where you'll find Fusion 360. Uh-oh, what's this? $85 a month? Or $680 for a year? Get the f*** out of here. This whole channel is about doing stuff on a budget. Last thing we all need is another monthly payment. Luckily, there is also a free version available for non-commercial and personal projects, and that is right up our alley. Now let's search for Fusion 360 Personal. And this is the option that you would need to download and get installed. Inside of the software, I will quickly draw up my bracket, and for the sake of time, I'm not going to go into detail on how I did my design. There are plenty of YouTube tutorials that would cover that. Instead, let me explain why this is the program I'm gonna use to cover our CNC plasma cutting needs. Fusion 360 has a couple of programs rolled into one. First and foremost, CAD, or Computer Aided Design Software. This is where you would draw up your part, just like in Tinkercad that we used earlier. Also, this is where the DXF file that is needed for our next step is being generated. And here is where we get into CAM, or Computer Aided Manufacturing, where we tell the CNC plasma table on how to actually make the cut. As far as how fast the torch should travel, also where and how the cutting begins, whether the torch is traveling clockwise or counterclockwise while making the cut, because believe it or not, that actually affects the outcome of the cut. Also, when and where to lift or lower the torch if your CNC table is equipped with a Z-axis. Or in our case, since we don't have a Z-axis, we can tell the program to move the torch around the areas that had already been cut in case that one of the cutout components tips upward. This way the torch is not gonna crash into one of those components, and instead it would just avoid traveling around the areas where the cuts have already been made. And lastly, let's jump into a post-processor. This is where the toolpaths are turned into a G-code, which the CNC table will read and turn into actual physical movements. And our post-processor of choice is this OpenBuilds CNC, the same program that you saw me use earlier on the laptop. It is not part of Fusion 360, these two programs just work together. To get your copy of OpenBuilds, go to openbuilds.com. Then navigate to Software tab and choose OpenBuilds Control. On this page, hit the red download button and install this software on your computer. The one setting I want to go over in this tab is the pierce delay, which is currently set to 1 second, and 1 second is good, so I'm not going to change anything. And finally, once I hit post, we get our G-code. Not gonna lie, when I first laid my eyes on it, none of it made any sense. But after researching it for just a few minutes, it became quickly apparent that there is really not a whole lot to it. And in fact, it's actually pretty simple. As I'm filming this video, my original plan did not call for a deeper dive into a G-code, but I ran into some issues while making my cuts, and the way I was able to fix them was to go into my G-code, figure out what the issue was, and find a workaround. The very top of the G-code just goes over some general information like about the post-processor that we're using and some other basic settings that we don't need to change. But the important part of the code starts right down here. First line that starts with G0 followed up by some X and Y coordinates is the starting point of the cut. Don't mess with it. In the next line down, the M3 code fires up the torch. Don't worry about the S1000 code. In our case, it's not important. But G4P1 in the next line down is important. G4 is command for dwell, or basically pause, and P1 stands for duration of 1 second, because pierce delay of 1 second is what we chose to be in a previous step. And the next line down that starts with G1 and some coordinates after that is basically telling the plasma table to start moving through the X and Y coordinates. Another important bit of code is this F1350. And that is how fast the cut is being made. In this instance, it is 1350 millimeters a minute. And so on until we get to line M5, which is basically telling the plasma cutter to stop firing. Now let's sum up what we just learned. G0 sends the plasma table to the starting point of the cut. M3 is telling the plasma cutter to start firing. G4P1 pauses the plasma cutting torch for 1 second in one spot until the plasma arc cuts all the way through the metal. Then G1 with the following coordinates is telling the plasma table where to make the cut. At 1350 millimeters a minute, once the plasma torch gets to the end of the cut, M5 command will tell the torch to shut off. And then it continues from there. Plasma torch gets sent to the new coordinate, fires up, makes the cut, stops, goes to the next spot, and so on. The code basically repeats itself by giving the plasma table a new sets of coordinates for every cut that needs to be made, but the settings such as starting and stopping the torch, pierce delay, and travel speed stay the same unless you change them. And that is why I wanted to go into G-code to show you guys how everything is set up. So this way, if you needed to change something on the fly, you have the tools to do it. And that will become apparent here in just a minute. We got 3 cuts here, and all 3 of them are quite a bit different. On the first cut, we didn't even get any penetration, so I had to abort the process halfway through. And the reason we didn't get any penetration is because our setting for 1 second delay did not work. Literally, that setting simply did not take any effect. At first I thought that maybe 1 second of pierce delay is simply not enough to bust through a 1/4 inch plate. And for the sake of experiment, I changed it to 3 seconds. Let me demonstrate what's going on with that 3-second delay, and I'll go ahead and set my microphone right next to the torch activating relay. I turned off the plasma cutter so you guys can get a better idea as to what's going on here. As you can see, torch moves into position, but then instead of firing and dwelling there for 3 seconds and then starting to make the cut, it just sits there for 3 seconds. Then you hear a click of the relay that would indicate that the torch got triggered to turn on. And then without any sort of delay, it starts moving into the cut. So basically the delay happens before the torch activates, not after. I don't fully understand what's causing that issue, and maybe I will figure it out down the road, or maybe some of you guys could chime in and let me know what the solution is. But in the meantime, I did find a workaround. This is where basic understanding of G-code is starting to pay off. Right away, you can see our updated dwell time of 3 seconds. And now let's go ahead and add one more line of code between the M3 and G4 lines. G01 space F1. All that this command means is to start moving in a straight line at 1 millimeter per minute. I don't know why it works, but it does. And with this workaround, we no longer have a need for a 3-second delay, so we can change it back to 1 second right here within the G-code. And now we have to copy and paste the G01 F1 line for every start of the cut within the G-code that is represented by this M3. And since I'm manually adding stuff in, I'm also going to manually change the pierce delay from 3 to 1 on every G4 line. With this workaround, my pierce delay finally works just the way it was intended to. And guys, I do realize that this is not the most elegant solution to the problem, but at this time, until I figure out a better solution, this will just have to work. Another thing you can change right within the G-code is your cutting speed, especially when it comes to cutting circles. If you slow your speed down, you will get a better quality cut. And as far as cut speeds go, this is something you're gonna have to play around to kind of dial things in, because different plasma cutters with different cutting torches with different amperage settings will act differently. Pick up the speed on some thinner metal, but do slow down whenever you're cutting through some thicker stuff, and you will see that your cut quality will improve. One more thing I want to mention, my plasma cutter maxes out at 40 amps. So instead of playing around with all of the different amperage settings, I just set my machine to maximum amperage, where the only thing that I have to change is the cutting speed. And this right here is a perfect example. 2 identical cuts with the same amperage settings, where the only thing that I've done different is I've slowed down my cut speed while cutting out this piece. And would you look just how much less dross there is just because I slowed down my cut by 20%. Whereas on this bracket, the cut speed was just way too fast, so it remained partially fused to the panel that it was being cut from. Guys, it's me, from the future. Well, from the future to my past self that you just saw a little bit ago in this video. Remember what I said earlier? Maybe I will figure it out down the road, or maybe some of you guys can chime in. Well, never mind that. I got some great news. I figured it out. That workaround with G01 F1 code is no longer needed. But I think I'm going to leave it in the video because you never know, it may still be of some value to someone down the road. I had to do some digging, and in the end, the solution was actually much simpler than I thought. It all has to do with the fact that we are using a laser engraver for our plasma cutter. And that's probably what OpenBuild software detected when it connected to the laser engraver. So it went ahead and applied some default settings that would normally be used with a laser. And since we're not piercing anything with the laser does not need any pierce delay. And our fix lies within the OpenBuilds. Let's go ahead and jump into this log/serial console tab. This is where all of the default settings live. And just as I thought, OpenBuilds knows exactly what equipment we are using, and now we need to find a setting for a laser enable and disable mode. And here it is. $32 = 1 is a laser mode enable function, where the number 1 indicates that the laser mode is enabled. And to disable it, we need to switch number 1 to 0. For that, we need to drop down all the way to the bottom of the page and type in the updated value. Then hit enter. To reload and refresh the settings menu, type in the $sign twice and hit enter. And now if we scroll back up to the $32 line, we see that our updated value has taken effect. Another piece of equipment you need to run a plasma cutter is an air compressor. If you've used air compressor before, then you know that there is moisture and sometimes straight up water that would come out of the end of the hose. What is plasma? In this instance, think of it as concentrated fire. And what's that one thing that does a really good job putting out the fire? It's water. So if we have moist air or even water coming out of the end of the hose, we are going to cool that plasma arc, and that will greatly affect our cutting ability. That plasma arc needs to be as hot as possible to slice through that metal, just like a hot knife through butter. Because if that knife ain't hot, it's not gonna cut that butter too well. So it is extremely important that the air that enters the plasma cutter is as dry as possible. And this is something that I have personally already handled. The air that comes out of my compressor is very dry. I actually built this air compressor about 3 years ago. I did a video on that build and it became the best performing video on my entire channel with over 3 million views. If you haven't seen it, I would encourage you to take a look. It's got a lot of great information. What sets my air compressor apart from most anything that you'd find out there is this air pre-cooler. When air pump compresses the air, that air gets really hot. And once that hot air gets pumped inside of a cold tank, moisture in that air will get condensed and it'll settle at the very bottom of the air tank. And that's why the water needs to be periodically drained out of the bottom of the tank. In my case, water in the tank is the thing of the past. Once the air gets compressed in the pump, instead of going straight into the tank, it actually travels down this copper pipe down into a water bucket where I have a cooling coil and also an automatic drain valve at the very bottom of the coil. So that hot air cools inside of that coil on the way down, and then the moisture that settles at the very bottom in a form of water gets expelled through that purge valve down there, and the air that makes it out of the bucket through a secondary air-water separator only then makes its way into the tank, and by the time it makes it into the tank, it's already at the same temperature as the tank itself. I explained in great detail on how I built this pre-cooler, so make sure to check out the compressor build video. The whole reason for designing and cutting out this random shape was just so I could dial in some of the basic cut settings. And the settings for my last cut are the ones that gave me the best cut quality so far for this thickness of the metal. So those are the settings I'm gonna use to cut out something useful. The ram on my press brake is a bit slow to retract, so I thought that I would design and cut out this bracket, which coupled with some springs should really help that ram out. 1/4-inch plate, virtually no dross whatsoever. And the only dross that you do see here is the pierce dross, and this stuff just flakes right off, so the amount of cleanup that this flange required was absolutely minimal. The cut is very even and uniform. Cutting thinner material is not all that hard, not to say that a 1/4-inch steel is all that thin, but let's go ahead and step it up a notch and push my plasma cutter up to its limit. I'm curious to see how well the plasma cutter and the plasma table can handle this 1/2-inch steel plate. Plasma cutter consumables, such as nozzles and electrodes, wear out the most during the piercing process, and my understanding is the thicker the metal, the more the wear and tear is. So to prolong the life of my consumables, I'm not going to pierce this 1/2-inch plate, but instead I started the cut from the outer edge. There was more dross on the sticker cut, but removing it was easy and it took no time at all. The cut quality really did surprise me. I honestly did not think that it was going to turn out this good, but in this case, results do speak for themselves. Let's check for beveling. Let's see what the deviation is between the top of the circle and the bottom. So about 30.7 millimeters. And if we flip it over, 30.5. So the deviation is only by 0.2 of a millimeter, which is almost nothing. And I think that this type of a cut is more of a testament of a good quality torch rather than the main unit of the plasma cutter. And no sooner that I get my plasma table built, I get my very first paid gig. This is Mike.
Hey, Mike, you're gonna be in my video.
Mike is a truck driver, and these pins go somewhere on a trailer of his semi-truck, and I guess he keeps on losing them, so he asked me to make him some extras.
It looks pretty easy, right?
That's right, it is going to be easy, because now I have the tool that would help me tackle the hardest part of this whole build, which is making these top plates. This is the bracket that I cut out a little bit ago, and check out how well this thing fits. There's just a very tiny bit of slop there, and that's exactly what I was going for. I went ahead and welded these pins up off camera. And this bracket you saw me cut out earlier is going to find home on this slow to retract press brake. This thing just takes forever to suck the ram back in, and most of the time I have to help it out. And the plan is to do something like this. I'm probably gonna still have to modify some things to make it work. This design of mine is still not finalized, but you get the idea. In the end, I made few more small modifications to this table just to make it a bit more user-friendly. I first lengthened the limit switch and ground wires you just saw me remove. Next, I 3D printed this Allen wrench holder, so this way I don't have to worry about losing this Allen wrench since it is pretty small. After that, I applied a couple of strips of double-sided tape to the back of the torch activation relay. And I also added torch signal quick disconnect, which also received a strip of double-sided tape. And finally, the relay and quick disconnect both got stuck into their final resting place, after which the signal plug got connected. And last but not least, the torch trigger wires also received a corresponding quick disconnect plug. The beauty of this type of a portable setup is that once you're done using it, just unplug and detach the torch. This laser engraver weighs about 5 or 6 pounds. You can simply hang it up on the wall if you wanted to. This way, it's not taking up any of your garage floor space. This is not a perfect setup. It is not a full-fledged plasma table. It's pretty limited in size, it's not very rigid, and it doesn't have Z-axis. But it is definitely the cheapest, easiest, and fastest way to get into CNC plasma cutting. Most of you will probably be cutting out and making some sort of brackets to be used in your garage or some truck suspension. If you are just a guy in a garage who likes to tinker and build stuff, a weekend warrior like myself, then I don't see how a setup such as this one wouldn't satisfy like 90% of your needs. All in all, I was able to tackle this build over the weekend with a total expense of $550 into everything that you see here. And this is a perfect definition of a quick and moderately easy budget setup. Guys, I need some feedback. This video that you're watching right now is going to be the longest video that I've done on my channel to date. And my question to you is this too long? Because generally my videos are about 20 to 25 minutes long, and this one is just about double that. There was definitely a lot of information that went into this video, and I probably could have left some of it out, just to shorten things a little bit. Do you think that would be beneficial, or is this length good, or should I make my videos even longer to pack even more information into them? And my other question is, what do you think about this type of content? I personally love anything that has to do with anything CNC, but do you enjoy this CNC plasma table build? The reason I'm asking is I can actually make another video on the same topic, only next time I can take it even further. I can do a larger table with Z-axis and also THC, which is a torch height controller. If you don't know what that is, look it up. It's a pretty useful feature to have on your CNC plasma table. And as with all of my videos, I would do that build once again on a budget. Another important thing to note is that not all plasma cutters are created equal. For use with CNC plasma table, you absolutely have to use a non-high frequency plasma arc machine. The torch will never touch the steel, so it needs to have a pilot arc to bridge the gap. And it also cannot have high frequencies because that will disrupt the cutting process by causing your plasma table control board and even your computer to malfunction. But even a non-high frequency plasma cutter can still have some high frequencies, so it is beneficial to keep your plasma table control board farther away from the cutting area, even if it means that you have to lengthen some wires. I will leave links to a lot of the equipment that you saw me use in this video in the video description down below. If you guys liked the video, I would really appreciate it if you hit that like button and subscribed if you haven't already. And with that being said, this is all I got for you for today, and I'll be seeing you on the next one.